This video, I'm going to prove this lemma. It says that if you're given two positive integers m and n, and the GCD is 1, then the set of positive divisors of m times n consists of all products of this form, a product of d1 and d2, where d1 divides m and d2 divides n, and the GCD is 1. So all divisors of mn are of this form where d1 is m, d2 is n, d1 divides m, and d sub 2 divides n, and the GCD of d1 and d2 are themselves the number 1. If you like seeing mathematical proofs like this, you should consider subscribing to my channel, as this is all we do on this channel. We do mathematical proofs. Okay. So I'm not going to bother when m and n are 1. I'll leave that as homework. Assume m and n are both bigger than 1. So the cases I'm leaving out is when m is 1 and n is not, or when n is 1 and m is not, or they're both 1. Okay, so let's get right into it. Let m be p1 to the a1, p sub 2 to the a sub 2, all the way up to p sub r to the a sub r, and n is equal to q1 to the b1, q2 to the b2, all the way up to cube sub s raised to the b sub s power, where the pi's and qj's are primes. Since the GCD of m and n is 1, that implies that no p sub I equals some q sub I, q sub j, say. Okay, so now let's note this, that all positive divisors are of a certain form. All positive divisors are uniquely, say, represented in the following form. Let's call it D. So it's gonna be P1 to the U1, P sub 2 to the U sub 2, all the way to P sub R to the U sub R times Q1 to the V1, all the way down to Q sub S to the V sub S power. I proved that. Okay, wait, hold on. Where U sub I is in between 1 and a sub 1, a sub I, and v sub I is in between 0 and b sub I. That is, did I have m times n written anywhere? No. It's going to be this times this, where these powers can be anything from 0 up to a1, up to a2 for the base p sub 2, up to a sub r for this power. For the q sub 1 base, it can go up to p sub 1. That's what every divisor is going to be of the form. Okay. So now that we have that, what we can do is we can call that D1 and this D2. So let D1 be P1 to the U1 all the way up to PR to the UR, and D2 be P to the V1 all the way up to Q sub S to the V sub S. Okay. Now, clearly D1 divides M because D just has larger powers. You have P1 to the U1. Well, let's put real numbers in. Say you have the first prime to the third power, so I'm doing D1. And the second prime to the fifth power, the third prime to the fourth power, and say just 4 primes, and that's to the third power. Now that's going to go into P to the fifth, P1 to the fifth, 2, P sub 2 to the 7, P sub 3 to the 4, P sub 4 to the 11. Notice that this power is no bigger than 5, this power is no bigger than 7, this power is no bigger than 4, 4 is not bigger than 4, and this power is no bigger than that power. This is going to equal P1 squared times P2 squared. If I put P sub 3, the power will be 0. P sub 4 to the 8. And that is, this denominator really went into this. That is D1 did, D sub 1 does divide evenly into M. Okay, it goes in this many times, evenly. And the same thing for D2 dividing N. Okay, no magic there. The powers are no bigger in the D1 than in M. D1 is going to divide it. And likewise, D2 will divide N. Okay. And here's the end of the proof. Furthermore, the GCD of D1 and D2 is 1. Okay. Now, one way I can say it is they have different primes. You can also argue that since the GCD of M and N is 1, if you only take some factors of M and you take some factors of N, then their GCD of that pair will also be 1. That is, I'm replacing M with D1 and N with D2. Well, how on earth, that should say GCD, how can the GCD of these two be bigger than 1? Okay, because the GCD of D1 and D2, since D1 divides M and D2 divides N, this must be less than or equal to the GCD of M and N. But that's 1. And the GCD of any two numbers, the least it can be is 1. So in fact, it's equal. So I did show that there's a D1 that divides M and a D sub 2 that divides N, and their GCD is 1. That completes this proof. Again, if you're into watching mathematical proofs, subscribe to my channel, leave a comment, definitely click the like button. See you guys in the next video. Don't forget, watch and learn.